Hi everyone, we are a group of students from NUS. Chuan Xing, Arvin, Zach, Martin, and Chen Liang. Today we shall be telling you a short story on the sieve of Sundaram. Let's start with some background history. The sieve is discovered in 1934 and named after mathematician S.P. Sundaram from an East Indian village of Satyamangalam, which is a small town and sub-district in the Iru district in the Indian state of Tamil Nadu. The sieve was invented to obtain prime numbers from the universal set of natural numbers by literally separating the prime numbers from the natural numbers, and hence the name sieve. But before we talk about the sieve of Sundaram, we first need to understand what prime numbers are and their significance. A prime number is defined as a number that is greater than 1 and can only be divided by 1 and itself. Like atoms in chemistry, prime numbers are the basic building blocks in mathematics and all natural numbers. Every natural composite number or non-prime number is a product of two or more natural numbers. Interestingly, prime numbers occur frequently in the work of nature. For example, the North American cicadas in nature breed in a prime number cycle of 13 and 17 years to avoid synchronization with the reproductive cycle of predators who are likely to breed in periodic cycle of non-prime numbers multiple. Prime numbers also control the law of golden ratio, found in the arrangement of the branching of branches in plant stem, vein in leaf, skeletons, and veins and nerve in animals. This prime number controlled golden ratio, as discovered by Zinsing, also extends to the proportion and geometry of crystals of chemical compounds, and even to proportion in artistic endeavors and human beauty. Due to the mysterious significance that prime numbers have, mathematicians has long been fascinated with prime numbers and have been studying it for centuries. The earliest record date as far back as 3150 BC, to the time of ancient Egyptian. However, there was one big problem. Although the definition of prime numbers is so simple, it was difficult to derive prime numbers, especially the large ones, because they occurred in an increasingly sporadic manner and did not occur in any easily noticeable fixed patterns. As 18th century mathematical genius Leonhard Euler once said,
"Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the mind will never penetrate."
Over the centuries, mathematicians from Egypt to Greece tried to find an efficient method to derive prime numbers. Over time, prime number sieve, like Born sieve, Sierpinski's sieve, sieve of Eratosthenes, Waller's sieve, were created, but they were often extremely laborious. And then came the sieve of Sundaram. Sundaram's sieve was a huge advancement in the development of prime number sieve, and it was much faster and efficient than previous sieve. Presentation of sieve. So how does it work and why is it faster? Sundaram's sieve derived prime numbers by removing non-prime numbers in a radically different way compared to its predecessor. There are two parts to Sundaram ingenuity. The first part is that the sieve of Sundaram looked at the problem from a new perspective and greatly reduced the problem using three simple concepts. Sundaram's new approach was to sieve out the odd non-prime numbers instead of Eratosthenes' method of sieving out prime numbers. Hence, it doesn't require any prime before it can sieve out other prime as the sieve of Eratosthenes required. The three concepts used are as follows. 1. All prime numbers, except the number 2, are odd, and hence, all even numbers can be ignored. 2. The removal of odd composite numbers will leave behind the prime numbers, which are virtually all odd. 3. Odd composite numbers can only be derived from the product of two odd numbers and can never be obtained from a product with any even number. We'll explain why he did that. Even numbers are all multiple of 2 and cannot be prime numbers. Therefore, all prime numbers other than 2 are odd numbers. By using this first concept and ignoring all even numbers, the problem is effectively reduced by half. but we're still left with both the odd prime numbers and the odd composite numbers. To get only the prime numbers, we need to somehow remove the odd composite numbers. But before we can do that, we need to derive them in the first place. This is where the third concept comes into play. The sieve of Sundaram hinges heavily on the concept that you can only obtain odd composite numbers from a product of two odd numbers. The reason is simple. Any number, when multiplied with an even number, will become an even number. Example, 111 times 2 equals 222. 531 times 2 equals 1062. Since we have already ignored all even numbers, we can somehow derive all odd composite numbers and then remove all of them. We'll be left with all the prime numbers. This is where Sundaram worked his magic, in an easily understood, systematic, and accurate derivation of all odd composite numbers. We shall explain how it works. Let's assume that there are two odd numbers, p and q, in a form of p equals 2 times I plus 1 and q equals 2 times j plus 1, where I and j are also natural numbers. The two odd numbers are in the form of 2i plus 1 and 2j plus 1 because a natural number n is odd if and only if there exists a natural number n such that n equals 2 times n plus 1. To obtain an odd composite number n, we multiply p with q. This is how the derivation of the odd composite number will look like. Odd composite number equals p times q. Most people will have done with the multiplication with just p and q without looking deeper. However, Sundaram looked deeper than everyone else and he discovered this particular equation. 2i plus 1 times 2j plus 1 equals 2i plus 2j plus 4ij plus 1 equals 2 bracket I plus j plus 2ij bracket plus 1. Then we let n represent I plus j plus 2 times I times j. Now we can see that 2 times I plus j plus 2ij plus 1 is actually in the form 2 times n plus 1, which means that it is an odd number. 2 bracket I plus j plus 2ij bracket plus 1 equals 2 times n plus 1. Therefore, we can see that all odd composite numbers can actually be expressed in a form 2 times I plus j plus 2ij plus 1. So if we wanted to derive all odd composite numbers, we can derive them using the equation 2 times bracket I plus j plus 2ij bracket plus 1 by varying I and j. This is exactly what Sundaram did, and it is also the second half of Sundaram ingenuity. Remember when we mentioned there are two parts to Sundaram ingenuity? The other half of Sundaram ingenuity was in creating a simple two-dimension table of numbers. The numbers are in the form I plus j plus 2ij, in which the value of I and j increase across the rows and down the column respectively. It was a simple table that could easily be derived with a simple compilation, so that it would be hard for mathematicians to make compilation errors. This was a breakthrough for the time. We have to remember that when the sieve was created back in 1934, there were no supercomputers during that time to do complex automatic calculation. This is what it will look like.
Okay, good. Yeah.
Then we draw a second table. The value for the second table corresponds to the value from the first table. For column 1 to n of the first table, we multiply each value by 2 and then add 1 to the multiplication. As mentioned previously, 2 bracket I plus j plus 2ij bracket plus 1 produces odd composite numbers. Hence, the second table will be the table that shows all odd composite numbers. By removing the odd composite numbers from the second table and ignoring all even number, we are only left with the prime numbers. Even though 2 is also a prime number, albeit an even one, it has been neatly avoided by the assumption made that every even number except 2 is not a prime number. In summary, this sieve obtains a list of prime natural numbers by eliminating the odd composite natural numbers and even natural numbers from the list, given that every even number except for 2 is not a prime number. Motivations. As mentioned previously, Sundaram was an obscure Indian mathematics student. So obscure that no one has managed to fathom his motivation. We would like to ask him if we could, but he is most likely already dead. With a collection of great minds in our project group, we have narrowed down the possibilities. Our guess is that he was most likely either trying to do a maths thesis paper, or he might be simply be interested in the breeding cycle of birds and the bees, and some cicadas. But definitely we know that it was a pure love for mathematics that helped him through. However, we do know that the sieve of Sundaram has numerous applications. Application of sieve. The most obvious application of the sieve of Sundaram is for the derivation of prime numbers. The method that Sundaram developed is a remarkable breakthrough, and it is much simpler as compared to the arithmetic's exhaustive method. Running as a program, sieve of Sundaram is able to compute and produce the result faster than using the algorithm of sieve of Eratosthenes and the previous sieves. As prime numbers are used in many instances of our life, the sieve of Sundaram has many applications. Encryption codes used by Enigma machine by the Nazi German in World War II were created by the use of prime numbers. This was how it works. A very large composite number that is a product of two large prime numbers is used to store and retrieve the information. One must know the exact prime number. Hence, large prime number need to be generated to create effective encryption code. The use of the sieve of Sundaram to generate said prime numbers, encryption code can be created much faster and efficiently than before. In the modern world today, cryptography extends to the protection of passwords, credit cards, banking technology, and in fact emails are also sometimes encrypted to protect the information that is contained. Twin prime conjecture proof. On the academia side, the sieve of Sundaram finally made it possible for the academics to prove that the twin prime conjecture is true. At its most basic, the sieve of Sundaram is used for probability testing. Since the sieve of Sundaram utilizes the fact that odd composite numbers exist in the form of 2n plus 1 or 2 bracket I plus j plus 2ij bracket plus 1, the attempts to factorize the odd numbers are key to discover if they are prime numbers. In 2009, retired maths teacher Julian Haver introduced the sieve of Sundaram as a way to understand the twin prime conjecture much better. According to the conjecture, there exist infinite twin primes in the form of 6p minus 1 and 6p plus 1, where p represent a prime natural number and p plus 2 is yet another prime number which is greater than p by 2, as any prime number is of the form 6p minus 1 or 6p plus 1, the converse not being true. With the sieve of Sundaram, it will be easy to do primality testing for large numbers. Not only that, we can code the sieve of Sundaram into a program and use it for primality testing, especially since the sieve of Sundaram is a faster algorithm compared to the previous sieve like the sieve of Eratosthenes. Conclusion. The method that Sundaram developed is a remarkable breakthrough and is much simpler as compared to Eratosthenes' exhaustive method. Yet, it took a while for mathematicians to apply this newfound knowledge in the field, but when it was used, it punched a stamp on one of the oldest conundrums in mathematical history, the twin prime conjecture.